Do you see the CPU uses? Yeah, it's 100. So hello, I'm Piyush Raj and today I'll be talking about the devils of the loops. So other day I was talking with a friend and we were talking about something related to Nvidia while we stumbled upon a thing which was the problem of CPU uses. And I gave an example of how a loop could be a very deadly, like very dangerous thing, and how the CPU uses, which actually is being shown, is not really the thing which we think of. Like the CPU uses is a little different from what it exactly is. So let's see about it. What did we discuss? So I told him that a loop, a simple looking loop, something like this, just a loop. If you are a little bit familiar with Rust, you might recognize this devil. This devil is up here, these two lines, and this can be just made just like a line, just like that's it. The seven characters, these seven characters can be deadly, and how this bomb is being detonated is just executing it. So let me introduce you to a problem of infinite loop without any IO operations. So the problem is from something from like CPU cycles. If you are not very much familiar with what is a CPU cycle, I will tell you that a CPU cycle is just a clock in a computer. Like whenever there is a computer, there have to be a clock, whether it is a like microprocessor or it is a CPU or any kind of processor is it have a clock. You can just look at that a circuit, there will be a crystal oscillator, and what does that clock does is it will maintain a timing. Okay, and this timing is called a cycle, and one cycle can execute either one instruction or a pipeline of instructions. That really depends upon the architecture. Well, in current case, which is Intel, for me it is a pipeline of instructions. And what happens is whenever you have a loop and it is a CPU cycle, the process is being allocated as many CPU cycles as possible, because the loop won't stop for anything. It won't wait, it won't do anything to just like fulfill some kind of wait, that there will be gaps between cycles. For example, suppose there are multiple cycles going on, okay, and this cycle like takes something from one application, app 1. This cycle takes something from app 2. This cycle have to take something from maybe back 1 to app 1. Then this is app 2. So this is how the things should be scheduled, and there will be a scheduler for it. Okay, and if you just fail to allocate in this way, one application will get either more of the cycle or other application will get the more of the cycle, and it will make the whole thing very much busy. If you can just think of, suppose there is this more cycle going on for the app 1, then in that case you can think like app 1 is getting more resources, more timing, more attention, and this will just deprive the app 2 of attention. You can understand now. So that's the whole thing which actually shows up here in the uses. So what this uses mean is how many of the CPU cycles are being used, like utilized. Like if no one is waiting for a CPU, like no one is waiting for the IO or any kind of thing, then everyone, like someone would be using it like in a very regular manner, like just one after other. If you just see some kind of popular algorithms, like maybe scheduling algorithms. Yeah, so if you just look at some of the popular scheduling algorithms, like this one, first come, first serve, or shortest job next, and this kind of algorithm, you can just look at that. If like for example up here there are four processes, and then there are the arrival time of them, then there is this execution time, and we just allocate them one after one. And if there is like someone has to wait, then the cpu will go into the ideal state. Well, if there are more ideal state for the CPU, then the graph would look like something like this, which you see as an ideal, and we say it as an ideal case. While for the infinite loop, which doesn't do anything with the IO, it will be a really lots of cycles being executed one after one, and there is nothing to like wait it or get the CPU ideal. That's the problem. And let me show you up here. If you can just in this code, what we are doing is we are just like collecting, just taking the number of threads and executing as many as threads possible whatever we have given, and in all those threads I execute a loop. If I do it for one thread, if I do it from one for one thread, you can see any one of this will get to 100. You see, this is C7. This doesn't mean that that one will be the one which is getting to 100 always. You can see this time this is C5 or some, or even this at beginning it was C5 and now it switched. So that's how the scheduler is working. Well, with that in the mind, with that explanation in the mind, you might ask me, just think about it. If we have 20 like this all or not cores, I have 14 cores and few of them are thread, but suppose if they are 20 compute units, okay, for me, then I release the 20 threads, then all of them will get to 100. Okay, then also, can you see it's snappy? Why can I move the window? I said that if I don't stop the CPU, if I don't like, if I am doing lots of work and this CPU is very much busy, in that case there is like less time available for this other task. But why this task is like, why the moving of the window, which is a very intense task, is happening? Like it should be laggy, isn't it? Why is that case? Well, I do have another explanation for this, which is every task, every task, whether it is A or whether it A1 or whether it is A2, have some kind of priority. In like in any popular algorithms, whatever you can think of, there is some kind of priority for every task. For example, A1 have priority of 1, A2 have priority of 2. So if in this situation, suppose this have priority of 2 and this have priority of 1. Well, since A2 have less priority, then in that case A1 will be executed more. Okay, but suppose if A1 have a less priority and A2 have more priority, then in this case, whenever A2 wants to execute something, then in that case A2 will be given the charge, like, do the thing, don't worry, we'll find a way to just snip in you, like put the things and just squeeze somehow the A1 and put you inside there. So like drawing a window and this kind of task have more priority, so your system looks very much snappy. Well, coming with this explanation, you might ask me, so if I want the devil to capture the system, do I need to increase the priority? Well, that's the thing which you need to do. You need to increase the priority of your process. There are multiple ways to increase it, but for now I won't be doing it, since if I do something like this, I don't know what my CPU will do. or if you can just execute the empty while loop in this kernel space. In the kernel space, what is a kernel space? Well, talking about a kernel space, I will tell you there are two spaces. One is the kernel space and one is the user space. User space have all the user application whichever you can think, like Firefox, Chrome, this task manager, window manager, and any kind of thing. Most of the application, even the system D, which is the init service for a Linux system, those all are part of user process. When we talk about the kernel processes, those are the drivers or those are the functions which are provided by kernel. Well, when we talk about the kernel space, if we see at the kernel space processes, they have lots of privilege. They can just talk to IO device directly, just write the bit and do their thing. So in that case there is something called as interrupt. Interrupts are events. Okay, interrupts are events, and based on these events the kernel space have certain event listener, and that event listener will do their task. Okay, in this scenario, when we move the window, we have a mouse click. We have a mouse click going on from mouse that is outside this kernel space. But yeah, mouse is actually a hardware, so it have something related to firmware and things going on communication. Well, then it goes to the USB driver, and then it goes to the kernel, and it tries to just communicate that okay, some kind of event has happened, and then it sees that okay, there is a user process which is related to this particular event, which is listening to this particular event, and it have a higher priority, so it will just give the thing and ask it to get the work done. And about the scheduling, the kernel will try to give as much as time it is possible. Well, kernel is not whole much responsible for this kind of thing, but yeah, it have some way of internally managing the scheduling thing, which I need to look much further, research on this thing. But for now, as much as we can think of is there is some kind of executor like scheduler, and that scheduler gives a much better priority to this. Well, then the question comes, what kind of operations will trigger this devil and what kind of operations don't? So how, what are the operations? Like whenever you have an operation which doesn't do an IO operation, like either it doesn't wait for something or wait for IO or something like that, then it will trigger. For example, let's have like let a is equals to 10, let b is equals to 20, this kind of operation like assignment, or even the addition c is equals to a plus b. This kind of operation don't prevent the devil to come. Okay, I just anyways doesn't matter what we did. Okay, that doesn't prevent the devil to come. What I missed the semicolon somewhere. Yeah, so that doesn't prevent a devil to come. Can you see the devil again came again, 87 now? And this is interesting, this is getting interesting. And if you want to prevent such kind of thing, you can either do some kind of IO operation. For example, you can just like print ln. Yeah, this will stop the devil. See, can you see? This is coming, and well, can you see? It's like getting 100, 84, 87, then it might get 100 again. It's not a constant 100. So in our case, the IO, the wait for the STD IO is not that well. So what else can we do? Well, we have I think Hey, why don't I have a LSP? I think couple of days ago uh, I do need LSP. Well, if you are just looking up into this kind of thing, like how I'm using NeoVim to get my work done and what is LSP, then it would be very much interesting if you just write a comment and tell me that you want to know how to use a NeoVim, what is LSP and things like that. I'll be really uh, happy to tell you about those kind of things. But for now, let's have a duration of from like milliseconds. 100 millisecond would be good for me. And does this have any kind of unwrap too? I don't think it have any kind of unwrap going on, so let's run it now. Does it prevents the devil? And we can see the devil is gone. So when was the first time I discovered it? I don't have the code right now because it was a quite long ago. Even now we can spin the 20 threads and it doesn't call the devil. You can see. So it was like about 6 7 years ago when I was using libgdx and trying to make a game, and I was not sure what is a game loop. Okay, that draw function for a game. I didn't knew that it goes like in an infinite loop, and it was the first time I encountered it, and I started asking about it on a Stack Overflow, and I was like, what's happening if the game, if I haven't added anything and the game already ate up my whole CPU, what will happen if I add something? And they were like, it won't. And I was very much amazed how the things are there, and now you know the devil of the loops. Anyways, thank you.